Very good morning to all of you. My name is Rahul Kumar Verma, and title of the talk is Gravitational Data Aggregation Mechanism for Periodic Wireless Sensor Networks, and we termed our mechanism as a GDA for the short form. So, in this talk, I'll be covering these topics. First of all, I'll be covering about the characteristics of periodic wireless sensor networks, then the challenges in the PWSNs, and followed by the objectives of this particular paper and the proposed mechanism GDA and analysis of that mechanism followed by the conclusion. So as sir discussed earlier that what is the wireless sensor network and all the sensor nodes are really power constrained devices. So we cannot do a lot of computations or we cannot afford so much communication between sensor nodes. So in the periodic wireless sensor networks, basically sensor nodes sense the data in a period of time and transmit a collection of data points to the next hierarchical node, basically. So all these data is transmitted to the gateway through multi-hop manner. And there is certainly a possibility that a sensor node is sensing a very redundant information because the sensing environment is if it is changing very slowly, then it is highly probable that a sensor node is sensing the redundant values again and again. So the basic motive to reduce the communication cost or to reduce the number of message exchanges. So we will try to identify the redundant sense data and try to eliminate those redundancies and send only the most appropriate values to the next node so that the most valuable information will be reaching to the gateway. So in that way, we will be reducing the number of messages and we will be reducing the number of communication costs. So this is the overall theme of this presentation. So this is the small figure that shows in the right side you can see the time, and there are three periods I've taken in this figure. Let's say P1, P2, and P3. So in each period, each period is divided into a finite number of slots. In each slot, data is sensed. So S1, S2, S3, and S4. These are the data points which is sensed in a particular period. So all these data DI11, DI12, DI13, and so on. This is the collection of data points in a particular period, and these collection of data point will be transmitted to the next hierarchical node, which can be the cluster head in the clustering technique, or it can be a parent node if you are taking the tree topology kind of thing. So in this way, all these collection of data points will be transmitted further to the gateway. So these data points, I'm trying to say that they can be redundant. So I am proposing a mechanism which can identify these redundant data points on node itself. Okay. So these are the basic challenges I've told earlier. So in the existing mechanism like cluster topology or clustered aggregation in the tree topology, sensor nodes does not care about what you are sending basically. So whatever the nodes are sensing, they keep sending the data without analyzing whether it is redundant or not. So we are adding intelligence on a node just to identify whether the data is redundant or not. So these are the challenges just to decrease the number of transmissions. So this is the basic objective of this paper for on-node identification of the redundant data points to conserve node's energy. And as sir told earlier, that most of the energy of a node is consumed in the transmission and reception. So our motive is to reduce the number of transmission, and this can be done by reducing the number of data points. So this is the basic mechanism, gravitational data aggregation, which is inspired by the Newton's law of gravity. So this is the basic analogy between gravitational physics and our proposed mechanism, which is GDA. So we are using variables which are typically used in the gravitational physics, same as in our mechanism. So here, basically what we are doing, we are creating a center particle as in the gravitational physics. So first of all, the data points which are collected in the first period will be termed as the center mass. Okay, and the M2, which it is the mass which is rotating around rotating around the center particle, which is M1. But in our case, the M2 is the newly sensed data value, which is to be identified whether it is redundant or not. And V is the velocity in the gravitational physics, same as we are basically the similarity index in our GDA. and r is the distance between m1 and n2 in gravitational physics. And same is with the distance between in GDA. It is the distance between the newly sensed data point and the center particle, which is the collection of nothing but data points which is sensed in the first period. So this is basic analogy, and this is the basic the diagram which shows how these gravitational things work. So in the center, this is a center particle, and our particle is rotating around its orbit. So there are two forces which acts upon it. So first is the centripetal force, which is nothing but a gravitational force, and the other is the centrifugal force, which helps him rotating in the orbit. So for the stable rotation in the orbit, these two forces should be equal. So on that basis, I'm equaling these two forces and identify what should be the velocity, optimal velocity for a particular object to rotate in the stable orbit. So this simple mechanism or this same concept is inherited in our mechanism. So first step in the GDA is the initial building of the center particle. So center particle is nothing but the data points which is sensed in the first period, just to initialize from something. So we take all the data points collected in the first period itself. And next is the initial velocity assignment to all the data points which is sensing in upcoming periods of the time. Let's say from period P2 onwards, every sensed data point has to be allocated by a velocity, particular velocity, which is calculated by this equation. As I showed you earlier, the equation is same, where m1 is the average value of the center particle, and r is the distance between newly sensed data point and the center particle. So it gives you the velocity basically, if I compare with the gravitational physics. And the next step would be, we will select the first one nearest neighbor of m1 in the set of data points. So let's say if in the second period of time I have 10 data points. So among the 10 data points, I will select the nearest of the center particle, and I will include that point into the center because it is the nearest. So it is the highly chance that it could be redundant. So after inclusion of that data point in the center particle, the mass of the center particle will change. So that's how the change in the mass of the center particle will instigate the change in the behavior of the other particles orbiting around the orbit. So that's why we have to update the distance and update the velocity based on the change that is instigated in the center mass. So the change in the velocity can be calculated by this equation. This is the normal equation, and the force that we can identify through the simple physics thing, A equal to F upon m, and the force is nothing but the difference between two forces which were acting upon the particle which is orbiting around. So as you can see, there are two distances, r and r dash. So r is the previous distance previously, and r dash is the newly distance after inclusion of the data point in the center particle. So if you can say if r dash means the new distance is increased, that means the a will take the positive value and it accelerate the particle. So as you know, if a particle is accelerated, then it can fly off from the orbit. So, and if the speed is decreased, it's gonna come into the center, towards the center. So depending on the speed of the particle, the inclusion or flying off from the orbit is decided. So if a data point is more of the redundant, it's gonna come into the center, and if it is not redundant, it's gonna fly off the orbit. So this is how we are basically differentiating between the redundant and the non-redundant data point. So as I said earlier, so based on the velocity, if the velocity is less in the after updation, so it is going to be included in the center particle. OI is nothing but the center particle, the collection of data points. It is going to come into the center, and otherwise it is going to fly off from the orbit. So it will be collected into TIK. So all these mechanisms will be repeated for all the data points. So all of these process will be followed for all the data points which is collected in the particular data point. So at the end of this mechanism, we have two sets. First is the center particle, which is nothing but the redundant data points, and another is a TIK, which is a non-redundant data points. So at last, for a particular at the last of the particular period, we will send the data points which is in the TIK, okay, which is nothing but the non-redundant data point. So this is how we have achieved this percentage reduction in each time period in sending the data. So variation is there because we cannot justify that how a data looks like. So we take the data from the internal research lab and perform and applied our mechanism to identify how much percentage reduction we can gain by applying this mechanism. So for different number of sense data points like f equal to 10, 15, 20, we applied this mechanism and achieved these results. And at the concluding remarks, it is on-node data detection, on-node computation mechanism that helps in reducing basically number of message exchanges, and it is far most required in the wireless sensor network because you cannot afford to send all the data to the gateway. So our focus is on offloading the computation towards the node itself, and the lightweight computation mechanism is required to be put on the sensor nodes to achieve all these things. So that's it. And one more thing I would like to add. See, as I said earlier, that we are trying to identify the redundant data values. So the non-redundant data value does not give you the does not give you the the context of that point. So the non-redundancy can be due to any change in the event, or let's say there is a temperature sensor in the room. So let's say at the normal point of time it is sensing 30 degrees Celsius, and suddenly it sends 50 degrees Celsius. So it can be due to the malicious behavior of that particular node, or it can be due to actual event that is taking place at the particular event of the time. So our next focus is on to identify the context of that particular variation in the readings. So whether it is actually a event or whether it is actual a outlier, basically. So this is the add-on to this mechanism which we are working on.